Hello! We're going to solve a word problem and we're going to use calculus to do it, but I'm not going to tell you exactly what word problem it is. First thing I'm going to do is I'm going to read it instead of writing it out on the board and then only having one board and then having to erase the board, which might be tedious to do and watch. But you'll be able to find the word problem in the comments. So this is the word problem reading out loud. Find the point P in the first quadrant on the curve y equals 1 over x squared, such that a rectangle with sides on the axes and a vertex at P has the smallest possible perimeter. So if you need to, pause, read it on your own, kind of try and understand what it's talking about. And the first step for us is always going to be a bit of a sketch where we lay out the things that we know, the things that we don't, and the things that we're supposed to find. So here in the sketch that I've already laid out for us, we have the first quadrant very messily drawn out. So here is the x-axis and the y-axis because we're going to have to make something out of them for a rectangle. And here is the curve 1 over x squared, or at least that's kind of what it looks like, right, in the first quadrant. So we are asked to find the point P, so there's going to be a point somewhere in this first quadrant, and it's going to be on this curve such that the rectangle with sides on the axes and a vertex at P has the smallest possible perimeter. So to construct such a thing, we would put maybe a point P here. So let's say that this is an XY point that is P. And then, if you want to make a rectangle out of this, we would do so using the x and y axes as the sides of the rectangle and that one vertex at P. So I think we've translated the word problem into a picture fairly well. So this is the rectangle that I'm talking about right here. So at this point then, we might as well look into what we have to do. It says find the point, so which point is it on this curve that gives us the smallest possible perimeter of this rectangle. So, for example, is it a really high, thin rectangle with the P being somewhere up here, or is it a really kind of a low rectangle that's kind of wide with P being down here, or is it somewhere in the middle? Who knows? We have to find the point itself. So what we need to do is minimize perimeter. So perimeter, I'll call it capital P. And now we realize that this is a max-min optimization word problem because we're being asked to minimize something. And if you realized that before, well, that's for the best. But if you weren't too sure, at least now you know. So we're going to go into this first by finding a formula, which we would always do, whether it's a related rates problem or a max-min problem. But the formula that we need is going to be for the perimeter, P. So P is equal to, when discussing a rectangle, twice the length measurement plus twice the width measurement. So 2L plus 2W, I guess. And what we need to do, though, is we need to find the measurement in terms of x. Because this is the x-axis, the curve is going to give us the height, 1 over x squared, of our point P. So if everything's in terms of x, we'll be able to find x and therefore find the point. So what is the length of this rectangle? Well, I'm going to say the length is this. So this is going to be my length. And the width, I'm going to say, is this. So length times height, I guess, or width, or whatever you want to call it. So that means that I would sub in an x for the L. And the height then, well, what is it? Well, whatever x is, that height is going to be at 1 over x squared. So it'll be 2x plus 2 over x squared. That is a 2, not a z. So now we have everything that we need to continue. And at this point, I'd like to say that there are some times where you have a max-min problem and there's something where it's in terms of x and in terms of another variable, maybe a y or an h or an r or something, and you can't take the derivative of that yet because we're working with one variable and we want to go p prime and we can't yet, and you need another formula so often it's the area, in order to try and get rid of that extra variable. We did need to do that. Wasn't that awesome? All right. So then p prime, with respect to x, is just equal to 2 plus, let's see, nope, that's not going to be a plus. I'm going to try and do it in my head. So it's going to be a minus 4 over x cubed, right? Right. And now we have to find critical points. These critical points are going to explain to us, if we were to make a graph of this situation, dealing with what the perimeter looks like, at one point we're going to hit a maximum perimeter and then we're going to come back down. And it's not this graph here, it's the graph of whatever this is. Go put it in graphing software if you want to see it. And it's the calculus of curve sketching that's going to help us find that max, or in this case that min, that valley that's being formed in this curve, and at what point x is that happening. So the first step is to find where p prime is equal to 0. And that happens when 2 is equal to 4 over x cubed. So 2 is equal to 4 over x cubed. And then keep going with this, because at some point soon you're going to have to stop and erase the board. So don't let me slow you down. But if you just move things around, then we get that gives 2x cubed is equal to 4. And that means that x cubed is equal to 2. So at this point, let me get out of the way and let you finish up that solve. Just smallest perimeter problem. We're almost there. So, good news. When you take a cubed root, there is no plus or minus, so who cares whether or not there was to begin with. If this was a square root, we'd have to logic it out. There's only one critical point where the derivative equals 0, and that is x is equal to the cubed root of 2. And an exact number like that is perfect for a test or exam or whatever you're doing. But you see, there's another critical point, and this is where a lot of us forget to be extra vigilant. A critical point is when you take the derivative of a function and you look at the derivative function, any point that causes the derivative to be 0, like this point, or any point that causes the derivative to fail to exist. And in this case, if we were to choose x equals 0, then 4 over x cubed would be undefined and this expression would fail to exist. So it's worth noting that p prime does not exist at x is equal to 0. However, at x equals 0, what kind of rectangle would we have? I mean, I don't even think that's a very well-defined rectangle. And as a thought exercise, I would have to ask you to actually imagine what that would do. So you'd have to, I'm not going to write it down because it's not part of the problem, but just take a second to think, okay, well, if x was 0, then I need to go up the y-axis to find my curve 1 over x squared, but then you never find it because the y-axis is an asymptote. So I guess you'd have this rectangle that it had like an infinite height or something. Blech. Okay, let's not think about it anymore. But that's the idea, right? At x equals 0, there's no rectangle. No rectangle exists. So we don't need to worry about the case, in this case, and often in many cases, where p prime or f prime fails to exist. But always check, just in case. So then we have our point x, and what we want to know is the perimeter function a minimum? I don't know what you can see. So is it a minimum if x is indeed equal to the cubed root of 2? Now, I can assure you that it is, but the way to check that is to search around there and see if you get a function p of x that dips down and then dips back up around cubed root of 2. So in order to do that, you have to argue what the sign of p prime of x is when x is less than the cubed root of 2 and when x is greater than the cubed root of 2. So look at this expression. If you put something in between 0 and the cubed root of 2 into this part, into this term, then it's going to be relatively small. Because, well, it's on this side of cubed root of 2, so it's closer to 0. So it's going to be relatively small, which will make this number relatively large. Which is a pretty neat argument for saying that then we're going to be subtracting off a lot, and therefore it's gonna end up being 2 minus kind of a bigger number. And the way to think about that is just think about a really tiny x, like if x was equal to 0.0001. There's no other critical points, so you can choose little sample points to illustrate that idea in your head. You're not going to have a calculator on the exam, right? So you have to get used to thinking that now. So then in this case, I'm saying it's going to be less than 0 when x is less than the cubed root of 2. And the argument that I also have is that if you were to put in a really, really big number, then this whole thing would be really small, so it would be 2 minus a little bit. So it would end up being a positive number. You can think of a really big number, like 100 or something like that, on this side of the real number line. So you are getting this kind of trend because the derivative function is negative on the left side of cubed root of 2. It's positive on the right side of cubed root of 2, and that gives you the geometrical situation that is a minimum. So that's when, just have to finish my thought here, x is greater than the cubed root of 2. Okay, awesome. So, coming back over here again, I'm just going to erase this now, and we can conclude. So if you're not sure what I was doing when I was going on and on about picking a sample point, take some time out, email me or ask somebody so you can clarify that, because this only took a little part of the board, but it took a lot of our thinking. Let's see, where are we? What do I want to do? All right. So, therefore, our point is going to be equal to the cubed root of 2 as the x-coordinate, and what's the y-coordinate? Well, it's 1 over x squared, because that's where we have fixed the point in the first place. So it's going to be 1 over the cubed root of 2 squared, which I suppose you could write as 1 over the cubed root of 4 if you wanted. And that's it. So I guess I'll just say, like, don't forget the case where your function derivative does not exist, because that's a critical point too. It may be a minimum, you never know. More than likely, though, it's a situation that's illustrated over here. And that's all we have to say about that. Well done.